Run your finger around a Lindor truffle. Go ahead, there's no seam, no injection hole, no mold line where two halves were joined. Yet inside, liquid chocolate that flows the moment your teeth crack the shell. But here's the crazy part. That sphere was never assembled. It was never two halves glued together. It was never injected through a hidden port. Lindt produces over 5 billion of these seamless liquid-centered spheres per year. And the process that creates them isn't chocolate making. It's physics that belongs in a centrifuge lab. The engineering question. Here's the problem that most people never stop to think about. If you wanted to make a hollow chocolate ball filled with liquid, how would you do it? Your first instinct, make two half shells, fill one, seal them together, but that leaves a seam. Lindor has no seam. Your second instinct, inject the filling through a tiny hole, then seal it, but there's no sealed hole either. The sphere is one continuous shell, born as a single piece, completed as a single piece, and inside, a filling that was liquid when the shell was solid. That sounds like it violates physics. But it doesn't. It exploits physics. The 140-year engineering lineage. To understand how Lindor works, you need to understand something that happened in 1879, 70 years before the first Lindor truffle existed. Rodolphe Lindt, a Swiss chocolate maker in Bern, was trying to solve a different problem. Chocolate at the time was gritty, rough on the tongue. No matter how finely you ground the cocoa beans, the particles wouldn't disperse evenly through the cocoa butter. The result was sandpaper, not velvet. One Friday evening in 1879, Lindt left his machine running by accident. A stirring mechanism inside a heated trough, paddles continuously folding chocolate back onto itself. He went home. He forgot about it. He came back Monday morning. The machine had been running for 72 hours straight, and the chocolate inside was transformed. Smooth, glossy. It melted on the tongue instead of crumbling. Lindt hadn't just made better chocolate. He had accidentally invented the conche, the machine that would become the foundation of modern chocolate manufacturing. Every smooth chocolate bar you've ever eaten exists because a Swiss chocolatier forgot to turn off a motor in 1879. Today, we step inside the production line where that same engineering DNA, precision, patience, physics, produces the Lindor truffle. A sphere so perfectly engineered that its manufacturing process hasn't fundamentally changed since 1949. Inside the system, spin casting. Every Lindor truffle begins the same way, not as two halves, not as a hollow mold waiting to be filled. It begins as a single, precisely measured deposit of liquid chocolate dropped into the center of a spherical mold. At this point, it's just a puddle, a warm, viscous puddle of tempered chocolate sitting at the bottom of a metal ball. Then the mold closes, and it starts to spin. Not around one axis, around two, simultaneously. The mold rotates like a gyroscope, tumbling in multiple directions at once. And here's where the physics takes over, but not just any physics, the physics of chocolate itself. Chocolate is not a simple liquid, it's what engineers call a non-Newtonian fluid, specifically a shear thinning fluid. That means its viscosity changes depending on how much force you apply to it. When chocolate sits still, it's thick, resistant, almost paste-like. But when you agitate it, when you shear it, it flows. The harder you push it, the easier it moves. This is not a footnote. This is the reason spin casting works. At 2,500 revolutions per minute, the shear forces inside that spinning mold are enormous. The chocolate, which would sit stubbornly in a puddle under normal gravity, suddenly becomes fluid. It flows. It spreads. Centrifugal force throws it outward, against every wall of the sphere. Equally, everywhere at once. Think about that for a moment. At 1 g, gravity pulls liquid down. But at the forces generated inside a spinning Lindor mold, equivalent to roughly 40 g at the mold wall, down becomes outward. The chocolate doesn't pool at the bottom. It coats every interior surface, top, bottom, sides, in a layer of identical thickness. Not approximately identical. Identical to the micrometer. In other words, the machine doesn't build a shell. Physics builds the shell. The machine just provides the rotation, and the chocolate's own shear thinning behavior does the rest. This is centrifugal casting, a technique used in industrial metal forming to create perfectly uniform pipes and cylinders. Lindt adapted it for chocolate. The shell forms continuously as the chocolate cools against the mold wall, building outward molecule by molecule until the desired thickness is achieved. Too thin and the shell collapses when you pick it up. Too thick and the ratio of shell to filling is wrong. You get a chocolate ball, not a truffle. The target? A shell just thick enough to survive packaging, just thin enough to crack instantly under bite force. Measured in fractions of a millimeter, controlled by rotation speed, chocolate viscosity, and cooling rate. The thermal window. Now the shell exists. It's solid on the outside, cooling inward, but the interior, the center, is still liquid chocolate. This is where the second engineering problem appears, and it's a problem of timing. You want the inside to stay liquid. That's the whole point of Lindor, but you also need to seal the sphere, and you need to do it before the entire thing solidifies into a solid chocolate ball. Here's the thermal tightrope. Cocoa butter, the fat inside chocolate, doesn't just melt and solidify. It crystallizes, and it has 6 possible crystal forms. Form 1 through Form 6. Each one forms at a different temperature. Each one has different physical properties, and only one of them is what you want. Form 5. The beta crystal. It's stable, glossy, snaps cleanly with that satisfying crack. Form 4 is what you get if you cool too fast or unevenly. It's soft, blooms white within days, and ruins the mouthfeel. Forms 1 through 3 are even worse. They melt in your fingers before reaching your mouth. The Lindor shell must crystallize into stable Form 5 on the outside, while the interior stays above the Form 5 crystallization temperature. That's a thermal gradient measured in single degrees, maintained across a distance measured in millimeters for a window measured in seconds. Too long. The entire sphere hardens. 5 billion solid chocolate balls. Too short. The Form 5 crystal network isn't complete. The shell collapses under its own weight when removed from the mold. The filling must be introduced at the exact moment when the outer shell's Form 5 network is structurally complete, but the inner layer is still above 27 degrees Celsius. Above crystallization. Still liquid, still waiting. This is not cooking. This is thermal engineering with a polymorphic fat as the working material. Pattern interrupt. The filling paradox. Pattern interrupt. I said earlier there's no injection hole. That's true, but the filling still has to get inside somehow. So let's address the question your brain has been forming since the beginning of this video. If the sphere has no seam and no hole, how does the liquid center enter a closed shell? The answer is that the shell is not closed when the filling enters. Remember, the spin casting creates a shell that's solid on the outside, Form 5 crystal, but still liquid at the core. At the precise thermal moment, when the outer layer is structurally stable but the center is still warm and above its crystallization point, the mold opens briefly. A dosing needle injects the signature Lindor filling directly into the semi-liquid core. Then the mold closes. Rotation resumes. The remaining liquid chocolate in the core, the chocolate that was always there, the original deposit, continues to crystallize outward from the new filling, sealing the injection point. The Form 5 network that was interrupted by the injection picks up exactly where it left off, growing new crystals that bond seamlessly with the existing ones. No hole, no seam, no plug. The shell simply continues growing, with the filling now trapped inside. The injection point becomes indistinguishable from the rest of the shell because it is the rest of the shell. Same chocolate, same crystal structure, same continuous matrix. In other words, Lindt didn't figure out how to put liquid inside a closed sphere. They figured out how to close the sphere around the liquid. Mid-roll CTA, but here's where it gets even stranger. The truffle exists now. Fragile, perfect, a micrometer precise chocolate shell containing liquid. Now it has to be wrapped, individually, in foil, at production speeds that produce over 150 truffles every second. If you want to know what's really inside the food you eat every day, subscribe. We go inside a new factory every week. The wrapping dilemma. The wrapping presents a mechanical paradox. You have a thin chocolate shell, barely thicker than an eggshell relative to its size, containing a liquid center, and you need to wrap it in foil. Tight enough that the foil won't unravel, gentle enough that the shell doesn't crack. Machines solve this with a double rotation wrapping system. Gripping arms grab each truffle individually. They rotate the truffle in one direction while simultaneously rotating the foil in another. The combined motion wraps the foil around the sphere without a single point of concentrated pressure. Think of it like wrapping a thread around a ball by spinning both the ball and the spool in coordinated motion. The forces distribute across the entire surface area of the sphere, never focused on one spot. The truffle emerges wrapped, sealed, and structurally intact. At the speed these machines operate, the individual wrapping motion is faster than the human eye can resolve. What looks like a metallic blur to an observer is actually a precisely choreographed mechanical ballet, executing the same motion 150 times per second across dozens of parallel lines. Quality control at scale. But there's one question I haven't answered yet, and it might be the most important one. 5 billion truffles per year, 13 million per day, 150 per second. Every single one is supposed to be a seamless sphere with a liquid center and a Form 5 crystal shell. How do you verify that? You can't open every truffle. You can't X-ray every truffle at 150 per second. You can't taste test a statistically meaningful sample without eating millions of dollars of product. So what do? The answer is a multi-layered quality system that catches defects before they become products. First, weight. Every truffle passes over a high-speed weighing cell immediately after wrapping. A truffle with a collapsed shell weighs less, the liquid center leaked out during wrapping, and the weight difference, measured in milligrams, is flagged instantly. A puff of compressed air kicks the reject off the line before the next truffle arrives. Second, laser profilometry. As truffles pass through the wrapping station, laser sensors scan the surface geometry of each sphere. A seam, a flat spot, an irregularity larger than 0.2 millimeters, detected and rejected in milliseconds. Third, and most elegant, acoustic testing. Some Lindt facilities use microphones at the cooling tunnel exit. A properly crystallized Form 5 shell produces a specific resonant frequency when it taps against its neighbors on the conveyor. A Form 4 shell sounds different, slightly duller. The microphone catches it. Another puff of air, another reject. What reaches the red box is not a random sample. It's the survivors of a gauntlet, weight, geometry, acoustics, that every single truffle must pass. The payoff. Let me bring this full circle. Pick up a Lindor truffle again. That seamless sphere, that liquid center, that perfect foil wrap, everything I've described. The 140-year conching lineage, the shear thinning physics, the dual-axis spin casting at 40G, the 6 crystal forms of cocoa butter, the thermal injection window, the acoustic quality gauntlet, all of it exists to produce one thing, a moment of surprise. You bite. The Form 5 shell cracks along its crystal boundaries. The filling, liquid, smooth, intensely flavored, floods your mouth, and your brain registers, this shouldn't work. How does this work? That moment is the product. Not the chocolate, not the filling. The moment of impossible geometry resolving itself on your tongue. And every single day, Lindt manufactures that moment 13 million times, using physics discovered by accident in 1879, perfected by engineers who understood that chocolate is not an ingredient but a material, and delivered to your hand by machines that exert less pressure per square millimeter than a human fingertip. The seam isn't missing. It was never there. Every Lindor sphere is a single, continuous Form 5 crystal structure, spun into existence by centrifugal force, sealed around its filling by thermal timing, quality checked by lasers and microphones, and delivered to you by wrapping machines that have been executing the same perfect motion since Harry Truman was in the White House. Here's what I want to know from you. Lindt has been making Lindor truffles since 1949 using essentially the same physics. The conching process since 1879. The centrifugal casting principle hasn't changed. The thermal window hasn't changed. The 6 crystal forms of cocoa butter haven't changed. In an industry that reformulates products every 3 to 5 years, that's nearly 80 years of fundamental process stability. Is the Lindor truffle the most perfectly engineered food product never to need a redesign, or is Lindt just sleeping on innovation? Drop your answer in the comments. I read every single one. Think about that for a moment. 13 million seamless spheres per day. Not one seam, not one injection scar, not one collapsed shell that made it to a store shelf. Tiny spheres. Massive precision. A manufacturing process so perfectly tuned that it converts 2,500 revolutions per minute of raw rotation into a moment of surprise. 13 million times a day. Subscribe for more deep dives into the engineering behind the world's most iconic products. And if the physics required to spin a chocolate sphere at 40G wasn't what you expected about you need to see what they're hiding inside a Ferrero Rocher. That video is on your screen right now.